Today we're going to go over complex numbers, um, talking about the imaginary unit of I. We're also going to talk about how to graph I on the coordinate plane, how to add and subtract complex numbers and multiply them. Then we're going to take a look at quadratic equations with complex solutions. So let's go ahead and get started. I'm going to share my screen here. And I'll copy the first problem to our screen. So this first one is asking us to simplify radicals using imaginary numbers. So here is the first question. It wants us to simplify this radical using the imaginary unit I. So there's a certain order for using I. So we have to use imaginary numbers because it's impossible to find the square root of a negative. If you type in square root of -1 in your calculator, you'll get an error message. So instead, mathematicians have found out that they can do the square root of -1 is equal to I. And we can continue this pattern as well. So now if we want to know, well, what's I squared? I squared is -1 squared, which is the same thing as -1 times, or excuse me, square root of -1 squared, which is the same thing as the square root of -1 times the square root of -1. So that's going to equal -1. I cubed, that's just I squared times I, because we add the exponent. So I is just I to the 1. I'm going to erase that though. And I squared is -1. And then we'll just do times I. So -1 times I is -I. I to the 4th is next. That's I squared times I squared. And I squared is -1 times -1. And that equals +1. So now let's take a look at I to the 5th. And these will help you with all of these problems. Probably should have started this before I even put this sample problem on here, but that's okay. So I to the 4th times I is I to the 5th. We just found out I to the 4th is 1, and I is just I. So I to the 5th is equal to I. Do I to the 6th next. That's I to the 5th times I. So that's I to the 5th is I times I is I squared. Now we have to go back here, and I squared is -1. We're going to do two more, and then you might see the pattern already. But we're going to go through what the pattern is after these next two. I to the 6 times I to the 6 we found out is -1 times I is -I, and I to the 8th is I to the 7th times I. I to the 7th we found was -I times I, and this equals -I squared. I squared is -1, so that's -1, which equals 1. I'm going to write all these out in a table now so that we can see this data a little bit easier. So our first one is just I. So I'm just going to say I is equal to I. Our second one, I squared is equal to -1. I cubed is -I. I to the 4th is 1. I to the 5th is I. I to the 6th is -1. I to the seventh is negative I, and I to the eighth is 1. And so we should see a pattern here. You go I, negative 1, negative I, 1. I, negative I, or excuse me, negative 1, negative I, 1. And this pattern will continue for every 4 exponents that this goes up by. Okay, so this is all the rules for I. If you don't have this in your notebook or somewhere saved, pause the video, take a screenshot of this, or write it down. So this is if you know all of these, really if you just know 1 through 4, you should be okay. But if you want to write down all 8 of them, that's a really good idea. I'm going to erase this now, but I'll leave the table there for our quick reference. And we'll also leave that negative root 1 is equal to I. So this is plus or minus root negative 14. Plus or minus on a square root that's just standard. We always get a plus or a minus with the square root, but we don't always see that in math. Because there's a negative there, that's like saying square root of negative 1 times 14. If we separate that, that's negative 1, root negative 1 times square root of 14. And root negative 1 is just I. So this is equal to I times square root of 14. And you write that shorthand I root 14. So that's how you do that part. We also have to check in simplified form if we can break down the 14 to anything more simplified. So we'll start with square root of 14 and find its prime factorization. You might have learned this without square roots before, using just regular integer numbers. But if you have, it's the same step as this. So square root of 14, we're just going to find all the ways to multiply to get 14. So this is square root of 7 times square root of 2. And we can't break square root of 2 or square root of 7 down any further. So there really isn't much more we can do with square root of 14. It's already in its most simplified form. So that's how we simplify that one. Hopefully we get to one that asks us to simplify. So I can show you an example there. The next one says square root of negative 100. And I'll just erase this actually. I was going to keep it on there and just go down the next one, but let's erase this. That way we have our table still. And we'll paste that here. Okay, so this is going to be the square root of negative 1 times 100, which is the same thing as square root of negative 1 times square root of 100, which is equal to I times square root of 100, or I root 100. Now let's see if we can break down the square root of 100 anymore. Well, that's actually kind of an easy one to do. Square root of 100 is just 10. But let me show you how it's just 10 when we do the prime factorization. Square root of 10 times square root of 10 is the same thing as square root of 100. We'll cross that 100 out because we were able to break it down. And I'm going to break this down further because 10 isn't a prime number. So let's break this down a little bit more. Square root of 5 times square root of 2 is the square root of 10. Square root of 2 times square root of 5, same thing over here. So we cross that out. Now square root of 5 and square root of 2, those are in their prime form already. They can't be broken down any further. So I'm going to write this all out like one math sentence now. Square root of 5. We can't forget our I also. I'm going to write the I first. That I right here, times square root of 100. That's going to be times square root of 5. Cross that out. Square root of 2. Cross that out. times that other square root of 2, cross that out, times square root of 5, cross that out. Now be careful not to just multiply this out again and say, oh, it equals 100. We're trying to break this apart so it's in a more simplified form. And what happens is this, when we multiply these two square root of 2's, we get, I'm going to write it on the side here, square root of 2 times square root of 2 is equal to square root of 2 squared. The squared cancels out the square root, and so now we're just left with 2. And you might have guessed it already. We have 2 square roots of 5 also, so that's square root of 5 squared, and that's just going to be equal to 5. So now we have I times 2 times 5, which is the same thing as 10I. Now, if you already knew square root of 100 is 10, you'd get I times 10, or 10I anyways. But I just wanted to show you how we're going to break down these numbers into their prime factorization form of radical form. So this one's going to be 10I. And we'll do one more very quickly. This one probably shouldn't take as long as that other one. So the last one we just did. Let's take a look here. The next one is square root of negative 55. Another negative, another imaginary number we're going to be working with. So now this is going to be negative 1 times root negative 1 times square root of 55. And square root of negative 1 is I. So we do I times square root of 55. Now let's see if we can break down square root of 55 at all. That's square root of 5 times square root 11. And those are both prime numbers. So this is just going to be our final answer for that one. Okay, this is I square root of 55. Okay, the next part of Unit 2 in imaginary numbers is powers of imaginary units. So this has to do with using our table now. So now we're going to look at our table and use our table data to find the power of these numbers. Our first question says, what would be equivalent to I to the power of 21? So here is our question. Let me just scoot this over. It says, what would be equal to I to the power of 21? Well, we're not going to go, I mean, we could do the pattern all the way to I to the 21, but let's think for a second how we can get 21 with powers of I. We already have through powers of 8 so far, so we could say I to the 8th times I to the 8th. That's already given us I to the 16th. And then to go from 16 to 21, we have to add 5. So we're going to multiply by I to the 5. Remember, we're always adding our exponents. So we're going to add all these, and that's going to be I to the 21. So now we can just go to our table and look and plug in what these numbers are. So we're going to look at these values, plug them in. So 1 is I to the 8th, 1 is I to the 8th, I to the 5 is I, and that's just 1 times I, which is equal to I. The next one's pretty simple. It says I to the 6. Again, we would just look at our table. That one's negative 1. Let's see if we can get a tougher one on here. Let's see. This is just a second. I'm going to find us a tougher question to do. Hopefully. Well, we'll just do one more here. This one says I to the 15th. I suppose that could be a little more difficult. But sometimes you might get some large numbers like I to the 54. I to the 100 something even. And if you just remember that you have every 4 repeats the pattern, then you should be okay with this. Um, so I to the 15th is I to the 8th times I to the 7th, or 1 times negative I, which is negative I. Okay. Now we're going to look at complex numbers. So complex numbers, they're numbers that involve I and a regular number. So complex numbers are written in the form A plus BI. Sometimes they're written with the I first, and then sometimes they're written BI plus A, but technically this is the way that we write complex numbers. If we look at our first example on complex numbers here, let me copy this. We actually they tell us BI first. So says, what's the real part of Z? It says, what's the real number part of Z? So, well, the real part is just 80. And the imaginary part of Z is the negative 60I. That's all one term there. So just type this in here. Oops, negative 60I. Might have to say, okay. So we don't include the I in the imaginary part. We just say the negative 60 for that. If you did type that in, I'm pretty sure you get a warning from the system, and it will fix it for you. It'll say you almost got it, but try again. So okay, here's another way that we can see the notation of the real and the imaginary parts. So here is just a moment here. Here's the next one. It says, what's the real part of Z and what's the imaginary part of Z? Well, the real part is 6.2 and the imaginary part is 37. So this is fairly straightforward when we look at how to do these ones. These aren't too bad. Um, and then you might get some questions that ask you with multiple choice instead of just typing in the numbers, but they're all the same thing. Next one is classifying complex numbers. I think this can be a little bit tricky because when I first did this, I'll show you this example here, and then it'll probably make more sense. When I first did this, it says, what type of number is 1024? Is it real? Is it imaginary? Or is it complex? And I said, well, it's a real number. It's 1024. But technically, this is also a complex number because if we write it in the form A plus BI, A is 1024 and B is 0, and 0 times I is just 0. But we can still say that 1024 is technically a complex number because it can be written in complex form. Let's look at one that's a little more reasonable with showing us uh, both the A and the B portion of A plus BI. So it says, what type of number is 12I plus 360? Well, that's a complex number. We know that because it's got the A plus BI, and that's all we have to do for that one. We'll do one more here. This next one says, what type of number is negative 91I? And give me just a second to paste that here. Negative 91I. Is it real, imaginary, or complex? Well, we have an I form there. That means that we've got the imaginary part, but it's also complex because A could be 0 as well. So it could be 0 plus negative 91I, or you could say 0 minus 91I. Oops, 91i. So either one of those statements would be true. All right. So I thought that one was a little tough at first because when first looking at this, you would just think, well, it's imaginary. It has the imaginary part. So just be careful with that part there. Now we're going to plot numbers in the complex plane. So what we're just going to do, I don't know, maybe we might just do one of these because it's very straightforward with the complex plane as well. So when we're looking at imaginary numbers in the complex plane, again, that's in the form of a complex number is in the form of a plus bi. The coordinates, though, are just a comma b, and that's equivalent to x comma y. So this coordinate, this value here is going to be negative 9 minus 7i. So a is negative 9 and b is negative 7. And that's going to be our coordinate. So we're going to go to negative 9 and negative 7. There's negative 7. And that's our coordinate, negative 9 minus 7i. This is definitely something you're going to see in uh, pre-calculus, maybe a little bit of physics as well, using the complex coordinate grid system. That's pretty much it. Oh, I guess we should maybe do one more example because sometimes they just have it in the form of when there's no A or there's no B. So let's do one more of these just in case. So the next one says plot negative 3i in the complex plane. Well, negative 3 is going to be our B value, but we don't have an A value. So A is going to be 0 and B is negative 3. And so that's just our coordinate 0, negative 3. That's 0, negative 3i. So this says real, and this is the imaginary plane here. All right. So actually we write it out like 0 minus 3i, but our coordinate, I should have just written it like this. The coordinate is still just like a normal coordinate that you see in everyday coordinates. All right, now we're going to look at adding and subtracting complex numbers. Adding and subtracting complex numbers is exactly like adding and subtracting um, uh, when we're combining like terms with algebra statements. So when we combine like terms algebraically, we can only combine things with the same letter and have the same letter and the same exponent value. So this is plus between those parentheses. We can automatically just drop those parentheses there. So we're going to combine like terms. Negative 21 minus 30 is negative 51. 65 plus 12 is positive 77i. And that's our final answer. It wants us to express it A first, then the BI form. So the real and then the imaginary form. 51 plus 77i. It's our final answer for that one. We're going to do one more. That one might have seemed really easy. This is some review that has to do with complex numbers and some algebra that would probably be a good idea to review. When we have a negative outside the parentheses, that negative goes to both of these numbers. It goes there and it goes there. So this is 7 minus 10i minus 3 minus 30i. Okay, so that minus has to go to both of them. If you just do on the minus 3 and you leave this a plus 30i, you'll get the wrong answer. So You can also think of it as like a negative one on the outside, and we're doing a distributive property like that. So that's why those parentheses are there. If there's a plus between the parentheses, don't have to do anything. You can just get rid of the parentheses altogether. So 7 minus 3, that's 4. Negative 10 minus negative 10i minus 30i is negative 40i. And it wants it in the form a plus bi. I think maybe you could put plus negative 40i. Let's see if that. Yeah, it'll still let you type in your answer in that way. If you want to write it that way, you can say 4 plus negative 40i also. That's another acceptable way to enter that answer. All right, now we're going to look at multiplying complex numbers, and we might get some where we have I squared. So let's go back up here and we'll copy this table. I squared is just negative 1, but we might have other ones where we get I to even higher power. So it might be a good idea to just have this table handy just in case. So here's our first one. This is really just, this one's not too bad. It's just one number using the distributive property with the i's. Just a second here to copy and paste this. All right. So negative 4 times 20i is our first step, is negative 80i. Negative 4 times 10 is negative 40. And that's all we have to do for this problem. I'm going to see if I can skip to some that are a little tougher because I think that's pretty self-explanatory. Okay, here's one that's a little bit tougher where we have i's in an I in more than just one term. So negative 3i times 8i is negative 24i squared. Negative 3i times 5 is minus 15i. And you might be thinking, well, now we have two terms, they both have I in them. We have to have a real number and an imaginary part. Well, I squared is equal to negative 1, so we have negative 24 times negative 1 minus 15i. That's positive 24 minus 15i. Now we have it in the form of a plus bi. Okay, so that's probably as much that we're going to get that section. Okay, now we've got some where we have to use the FOIL method. So we're going to multiply two binomials. Uh, we're going to multiply two binomials and they have a complex, they're going to have a complex answer. So we should have a total of 4 terms for this. And I'm just going to see if, okay. I was going to show you the shortcut for this, but I would suggest not doing the shortcut unless you're incredibly familiar with the shortcut. So do 4 times negative 5 is negative 20. 4 times 4i is plus 16i. Negative 2i times negative 5 is plus 10i. And negative 2i times 4i is negative 8i squared. So we can combine these I terms. And the I squared is negative 1. So I'm going to write negative 1, 8 times negative 1 right there. Now this is negative 20 plus 26i. Negative 8 times negative 1 is positive 8. Negative 20 plus 8 is negative 12. And we're left with 26i. 12 plus 26i. Okay, and all of these should be in the same format. Um, we shouldn't get anything that's greater than I squared, but if you ever do, it is possible if they gave us this in terms of like an I squared here and we had powers greater than I to the power of 2, you could go back and look at your table for this if you needed to. All right, let me take a look at this very last part here. Okay, the very last part of this is the quadratic formula. So the quadratic formula tells us the answers to where our graph is, where a quadratic or a U-shaped graph crosses on the x-axis. So if we have a graph that's like this, and we have a U-shape, these are the solutions or at the x coordinates. Now, sometimes a graph doesn't cross anywhere. Sometimes it crosses like um, up here, and it doesn't cross anywhere. But if we do the quadratic formula, we still end up getting an answer, but it has a negative square root in the answer. And so then we get i's in our answer. So if you remember doing the quadratic formula from other math classes, that's great. This will be good review. Um, if you just kind of remember, also good. If you don't remember or you haven't learned it before, that's okay as well. So the quadratic formula, first we make sure that our equation is in the form y equals ax squared plus bx plus c. That's the first thing that we want to do. And we can see that it is. So a is 11, b is negative 6, and c is negative 2. I like to write all of those out because I just like to try to be extra careful when I do the quadratic formula. And the reason is we have a lot of negatives that we have to do and a lot of multiplying that we have to do. Some students like to type it in the calculator right away. Personally, I really don't like to do it that way, but you can if you're really good at doing the quadratic formula, you can. So the quadratic formula is minus b plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times a. So now we're going to plug in all these numbers here. So minus b is negative 6 plus or minus the square root of, let's scoot this, no, I'll just leave it there, that's fine. B squared is negative 6 squared. Very important that you put this in parentheses. If you don't, in your calculator, it will tell you that negative 6 squared is negative 36, but that's not true because negative 6 squared is negative 6 times negative 6, which is positive 36. So make sure that you use parentheses for this. Minus 4 times A is 11 times C is negative 2. All divided by 2 times 11. Okay, so far so good. Let's simplify this a little more. Negative 6 is positive 6 plus or minus the square root of negative 6 squared is 36. Now this next part, we have 2 negative numbers left over. That means this is going to be a plus. 4 times 11 is 44 times 2 gives us 88. And this is all divided by 22. We're going to keep going. we have a plus or minus here, so it's going to give us those two answers that we're looking for. And 36 plus 88 is 124, all divided by 22. Okay, so far, I'm not seeing anything on here that shows us 124, but that might mean that we have to simplify things a little bit more. So hang on just a second here. And sometimes I make a slight mistake when I do the quadratic formula, so I'm going to double check that I did everything right. Okay, so everything looks good so far. We don't have a negative under the square root, so we can cross out C and we can cross out B because those have i's in the answer. This tells us that for sure our quadratic is going to have two real solutions that cross at the x-axis. All right, so now we're going to simplify square root of 124. Let's do that to the side here. 124, if we divide that, maybe we can divide it by 4. We can. So this is square root of 4 times square root of 31. Cross that out. That's square root of 2 times square root of 2. And cross that out. 31, that's a prime number. So now our equation is root 2 times square root of 31, or 2 square root of 31. So that's the prime factorization of, of the square root of 124. So now this equals 6 plus or minus 2 root 31 all over 22. This is saying two different things with the plus or minus. So we'll write out our two answers. 6 plus 2 root 31 over 22. And our other answer, 6 minus 2 root 31 over 22. Now, if we look at our multiple choice, don't see anything over 22. So that must mean we have to simplify this even more. So if we look at our coefficients and our constants, 6, 2, and 22 are the numbers we're looking at. And we can simplify this fraction. We can divide by 2 over 2. Let me write the divided here because we technically should put it over here. And we can do the same thing here too. So because there's a plus, we're going to divide that 6 and that 2 by 2. So 6 divided by 2 is 3. 2 divided by 2 is just 1. So this is 3 plus root 31, or plus 1 root 31, but we don't write the 1 there. 22 divided by 2 is just 11. And we'll write the other one there. 6 divided by 2 is 3. 2 divided by 2 is just 1. And this is minus root 31 over 22 divided by 2 is 11. So those are our two answers. You could also write it like 3 plus or minus root 31 over 11. You could also write it that way. So let's go back to our answer choices. 3 plus or minus root 31 over 11. And it looks like they wrote it in two separate fractions. That's another way you could write it, I suppose, is you could write it not as one full fraction line. So that's going to be our final answer for that one. Okay, so again, if you get a negative number inside of the square root, make sure that you bring an I on the outside. So if this said, this is a totally different problem now. If this was negative root negative 124, this would be I root positive 124. Then we would simplify, and that was the same thing as 2 root 31. So it would be 2I root 31. That's how you would simplify the square root of negative 124. Now, this had a positive, so we didn't have any i's, but this is what it would be if our answer had an I in it. If you have a negative, gotta take the I out and then still have to simplify and then multiply that I on the outside at the very end as well.